Hello students, so today's question says figure below shows a smooth track which consists of a straight inclined part of length L joining smoothly with the circular part. A particle of mass m is projected up the incline from its bottom. Find the minimum projection speed v for which the particle reaches the top of the track. Assuming that the projection speed is 2v and that the block does not lose contact with the track before reaching its top, find the force acting on it when it reaches the top. And the third part is, assuming that the projection speed is only slightly greater than v, where will the block lose contact with the track? So let's approach this question step by step, starting from the first part where we are asked to find out the minimum projection speed v for which the particle reaches the top of the track. See here that v has to be imparted over here at the lowest point of the track. See that for the block to be just able to reach the top of the surface, top of the spherical surface, it has to first travel till the inclined portion which terminates here, and it has to go further up a slight distance on the circular track also, isn't it so? So we have to consider the height of this track, the inclined track, as well as the circular track to find out the total height that the block has to reach. So if we take this point as the point B and the starting point as the point A, from A to B, if we can just find out the total height capital H which the block has to cover, see from the figure that this total height H will consist of this height, which is the vertical component of the length L of the incline, which will be nothing but L sine theta. And over and above that, there is an extra height that it has to cover along the surface of the sphere, which will be this height, which will be nothing but this length being r from here to here. And if we can easily prove that if this angle of incline is theta and we see that this is a radius, so this angle will be 90 degrees, we can prove that under this condition this angle will also come out to be theta. And if we know this, then we can say that this particular height will be r cos theta, so that the extra height that the particle has to move from the end of the incline till the point B will be r minus r cos theta. This particular small h is r minus r cos theta. So that the total height that the block has to move up, which is the sum of the height of the inclined plane plus the height of the extra spherical section, it will be L sine theta plus r into 1 minus cos theta. Okay, and this is the total height through which the block has to reach before it just comes to rest. Do we understand that the condition for the minimum speed for which the particle is just able to reach the top of the track means by the time it reaches the position B, it loses all of its velocity. That means all the kinetic energy gets converted into the potential energy. So we can directly use for the part A the law of conservation of energy between the points A and B, saying that all the kinetic energy at A half mv square gets converted into the potential energy at B, which will be mg into capital H. Just substitute the value of capital H here to get your value of V. So we see that V comes out to be root of 2g capital H here, and substituting the value of capital H, it will be root 2 g into L sine theta plus r into 1 minus cos theta, which will be your answer for the first part of the question. Now, the second part says, assuming that the projection speed is 2v and that the block does not lose contact with the track before reaching its top, find the force acting on it when it reaches the top. For finding out the force at the top, if we just consider this as the top of the spherical surface, understand that if we know the speed at this particular point v, then we can use the force equation on this particle, saying that the normal reaction acting upward and mg acting downward together will create the net centripetal force in the radially inward direction, which will be the downward direction here, and that should be equal to m into v squared by r, right? So essentially we are supposed to find out v, the velocity that the particle will have at the position B, let's call this velocity as v dash instead, because v is the initial velocity that we have assumed. So can we use for the part B the law of conservation of energy between the points A and B for the second case, where now the initial velocity is twice of this velocity that we have calculated in the first part. So according to the equation, then the kinetic energy at A will be half m into twice of v whole squared, right, where v is this velocity, and this should be equal to the kinetic energy at the top, which will be half m into v dash squared, if we assume that v dash is the velocity at the top, plus the potential energy at the point B, which will be mg into capital H. Now see that in order to find out v dash, we need to eliminate capital H here, and we can do that very easily using this particular equation, as we see that from here capital H can be written as v squared by 2g. So we can substitute that value here for H, v squared by 2g, and solve this equation for v dash. See that we will get, upon cancelling this half term everywhere, we will get, and m also will get cancelled, so that we have 4v squared on the left hand side is equal to v dash squared plus v squared. Yes, and that gives us 3 times v squared is equal to v dash squared. We get a relation between v dash and v. Now from here we can use the force equation at the point B. Force equation at B along the radially inward direction, which in this case is the downward direction. So that we write F net is equal to mass into centripetal acceleration at the point B, which in this case will be m into v dash squared by r, isn't it? Substituting the values, F net will be m into v dash, we have just now calculated here, it is 3 times v squared by r, and now we can substitute the value of v squared from the equation above. So we have 3m by r into v squared is nothing but 2g into L sin theta plus r into 1 minus cos theta. So that we can simplify this expression now to get the net force acting on the particle as 6 mg by r into L sin theta plus r into 1 minus cos theta, which will be the final answer for this particular part of the question.